Good morning. So let me continue this lesson. I know that there are some problems we haven't solved, but let us finish this lesson, and then I think we will have time to come back and solve some of those problems related to the related rates. Yes, do you remember? Okay, so that's a very fresh course, and that's very important and actually simple. So if you remember so far, we set up a table for finding derivative of different functions. But this is where you stopped in Math 3C. But now we want to actually add 4 more rows to this table. 3 of them we will add today, and 1 more will be left later. So this is probably the first time we officially want to know about the derivative of trigonometric functions. Okay, so today we want to answer 3 question marks and do some relevant problems. I want to know that if I put sine x in this column, what will be the answer? And I want to know what happens if I put cosine in this table. You might expect the next one is tangent, but for the tangent you have to wait a little bit. The next one is a logarithmic function ln. So we want to answer these 3 question marks together here today, and then we add 1 more function here, and that is the tangent x, of course. And then we will add 2 generic rules. You remember the addition rule, subtraction rule, and then the chain rule. We will also learn what happens for the product and the quotient. And then this chapter will be finished because the section on differential equation is eliminated from this course and it has moved to Math 5. So we will study that section in Math 5 but not in Math 4. Okay? So it means that if you don't have Math 5, that's a good news for you. So you don't need to study differential equations in Math 4 anymore. Okay, so I want to ask you now, this is the first question mark. My function is f of x equals to sine x. And now my question is that what is the derivative of this function? Okay, so let us review things. Now you tell me, where should I start from? If you tell me, where should I start from? Hello? Where should I start from? Yes?
Well, I mean, because I guess it's kind of hard to guess the definition of.
Yeah, it's definition. There's nothing left, Because if I want to know the derivative of a function which I don't know anything about its derivative yet, there is only one way, and that is just starting the definition. Yes? So how can I do that if I don't want to do it? So what I will do, I will follow the definition of the derivative. So if you don't mind, let me write it here. H goes to 0. And then, of course, you will face some problems here. I agree, but at the level of high school, we'll solve it in some way. If you want to find it in a rigorous way, you have to wait for the university instead. Okay, but let us see what happens. The first thing that I do, this is the formula that I have. I have to adopt this correct formula, this formula for this function. Fix it for this function. So minus sine is minus sine. F of x is on the right-hand side, which is sine x. And hopefully you have enough experience not to confuse this one. It means that go back to your function, take every x out and replace them with x plus h. There's only one x there. So if I do that, it becomes sine x plus h. And then I have h goes to 0. I have to do something to calculate this limit. First of all, don't get confused. 2 variables you see. One of them is x, one of them is h. But as far as this limit is concerned, x is fixed, h is variable. Because h is a number that I'm making it smaller and smaller. X is not given to me, but as far as this limit is concerned, is something fixed. But h, I can make it smaller and smaller, and to see how is it going. Okay. Okay, do you have any idea how to proceed? Yes?
Maybe expand this in...
Yes, we have the addition formula. So it adapts. Actually, it is really good to see that because we have the formula of sine u plus v. And then you remember, if you don't remember, I can of course write it. But at least you need to understand yourself. You have already seen that somewhere, yes? This is the sine of the first one, cosine of the second one, plus the other way around. Sine of the second one, cosine of the first one. Okay. And then, of course, I give the role of u to x, give the role of v to h. So, and then rewrite this formula for x and h rather than u and v. So this becomes the limit. Sine of the first one, in this case, is x, cosine of the second one, plus the other way around, sine of the second one, cosine of the first one. This is what I have written for the first term. Then I have a minus sign. Then I have my sine function. So I copied it and pasted that part and then divided by h. H goes to 0. Of course, this is a little bit hard to understand how to continue, but let us try to simplify things as much as we can. Okay, for example, I will take this one with that one and factor a sine x out. So sine x, and then I have cosine h minus 1. This, I just write it down. The only thing that I will do, if you don't mind, let me write cosine first and then sine, because that's a product, so it doesn't matter in which order I multiply them, yes? H goes to 0. And of course, you already know that if I have a plus b divided by one single c, if I want to, I can write a over c plus b over c, yes? So I will take this to be my a, and this one to be c, this one to be b. So I can write this divided by that, plus this divided by that, yes? So I will write it down. This becomes equal to the limit, okay, this one divided by that, I would write sine x here, and then I would write cosine h minus 1 over h here. Yes? Is that understandable? So I took this one and then divided by h, but because the numerator is product, I took this out and write only this divided by that. That is understandable, hopefully, because a times b divided by c is the same as a times b over c. And I will do the same thing here, but I write cosine outside. And the reason I'm doing it because I want to make those things we need transparent. And then h goes to 0. So I do not have any problems with sine x and cosine x because they don't depend on h. Whatever h is, they don't care. This is sensitive to h, this is sensitive to h. So it means that I have to calculate two limits, which is above. If I want to prove it rigorously, that is above what you can do at this level, rigorously. But you can, of course, understand that. So I need to calculate this limit, I need to calculate this limit. Okay. So I have two question marks to answer. One is this one, and the other one is that. Okay, I told you, we cannot do it rigorously. Of course, it is not extremely hard, but it needs some more theorems related to limits. But let us say that, okay, you don't have access to those theorems, but you have a calculator at hand, and then you have a limit, and you want to get a feeling for what that number is, this question mark and that question mark. You have a calculator, so what do you do? What do you do? Now come on. You don't know the answer rigorously, but you have calculator, and you want to get at least a feeling what these question marks are. what do you do with your calculator to get that feeling? Yes, you calculate that for very small numbers of h. Okay? And then find out if there is a nice pattern going on. Okay? The reason I brought this projector because I wanted to show what's happening. I'm lazy to do that. Okay, so this is given in your book. It's here. Okay, one thing is important, I will talk about that. So you see what they are doing here in this table. Let us consider this one first. They choose 0.1 and put 0.1 instead of h, and then they get this number. But that is extremely important. Switch your calculator to the radian mode and then do this calculation. I will talk about what happens if you don't do that a little bit later. Okay? So what you do, you first switch your calculator to the radian mode and then take, for example, h to be a small, say 0.1, put this in this, and then use your calculator to calculate, you get this number. And make h even smaller, you will get this number. Make h even smaller, you will get that number. Even smaller, you get that number. So based on the observation you see on this right column, what is your guess for the first question mark? No, first question mark is this one, 1. Yes? And do the same thing for the other function, you will get these numbers. What is your guess about this one? 0. Yes? Yeah, that's the only thing we can do. Don't expect me to actually calculate it rigorously. So here, this is the intuition that I get, that this is 1. And this is the intuition that I get, this is 0. But let me write it in radians. So that is extremely important. Yeah, but of course when I say extremely important, it doesn't mean that if you don't respect you will die. But it is actually extremely important in the realm of mathematics. Okay, so what happens? It's very simple now and very interesting formula. So this part is 0. This part is 1 because the limit of the sum is the limit of the first one plus the limit of the second one. This is a constant as far as this limit is concerned, so what I care is just number and that number. Of course, if I immediately ask you, I want to test your understanding. Let us ask you this. If I switch to degrees, do you think this will be affected or this will be affected or both of them or neither of them? So let us assume, I want to test just your understanding about the units. So if I switch to the degree mode and do the same calculation again, which one of these numbers do you think will be affected? Both of them, none of them, one of them? Yes? None of them. Okay. So if there's none of them, why should I say that this is important? So there should be some reason, otherwise it would also work in the degree mode, yes?
Like, I agree with Simon, but I happened to look at the graph of it, and it did affect at least.
Yeah, of course it will affect.
But otherwise it wouldn't be important.
But no, not because of that. Because sine of any number is a pure number.
Yeah, that is a degree.
And then, of course, if you have a degree, then you have a units for it, and that's different. We will talk about this. Don't want to. But this is clearly not affected, because if a number is 0 in degree mode, and in radian mode, it will remain 0 in another mode. Okay. But this will be affected. If you don't believe me, switch your calculator to degree mode and do the calculation. And it is not easy to guess that number. Okay. We can calculate that number, and that is one of the exercises in the book. Okay, let us not distract you for the time being, but I want you to make sure that this is important, that if it is in radian mode or in degree mode. Okay? Now, what happens if I put everything back in order? What happens? I want to answer the question mark, so if you don't mind, let us continue. Let us put this in a box. Use this information to calculate that limit. The answer is simple. Sine x times 0 plus cosine x times 1. And this is what? Okay, that is your beautiful formula. So the derivative of sine is just cosine. So we clean up this question mark and we write cosine x here. Okay? Yes, is that understandable? So the derivative of sine x is simply cosine x. Okay, before giving you some examples, if you don't mind, let us answer the second question mark, and I want to ask your opinion about it. Okay? How do you think it is good to calculate the derivative of cosine x? How should I do that? Okay, answer something, come on. I want to calculate the derivative of a new function cosine. So what should I do in principle? We do the same thing, yes? But there is one principle if you're a good mathematician, and that is being lazy. Okay, so this is important. Whenever you want to solve a problem, reduce that problem to a problem that you have already solved. Okay, you can of course start from scratch. The only difference is that you have cosine here and cosine there. And of course that is not a problem because you also have the formula for the cosine of the addition of the sum. And then you expand it, and then you will not face any new kind of limits. You will face the same limits. Okay, you get a number. But I don't want to do it in that way. If you want to practice, you can do it in that way, and then you find the answer. But let us try to see an alternative, because that is actually a good way of doing things. Okay, now I want to ask you again. That one way, I agree with you. If you follow everything as before, similar to before, you will actually get the answer. But if you don't mind, let us see if we can explore the derivative of cosine after what we learned about sine in a different way. But now my question is that, which way? Do you have any idea? I'm telling you again, this method will work. Okay? But let us not do that to understand things a little bit better. So, if you want to think an alternative way of doing the same thing. Any ideas?
We transform cosine x into sine x.
Using
Um,
complementary rules, yes?
yes.
Yes. And that is, still you don't have this feeling, okay? Sine and cosine are more or less the same thing. Do you remember the graph of sine and cosine? They are more or less identical except for a shift. And we have done this for over and over again in trigonometry course. Sine and cosine can be transformed into one another. Okay, so the first thing that I want to take the derivative of cosine. This is my question mark. But you know that, let me put this prime here. But instead of cosine, we learn I can write sine of what? Its complement. What is the complement of x? What? No, complement. No, complement is 90 minus x. So, yeah, this is very important. I don't know how you forget. Okay. So it is 90 minus x. But, yes,
Shouldn't be
pi over 2. Because what we learned for the derivative of cosine, as what was sine, was in radian mode. Okay? So, for the purpose of taking the derivative, I have to write pi over 2 minus x. Okay, at least this is clear that I have to use the derivative of sine. But the problem is that what I see in my table is sine x. But this is not sine x, this is sine of something else. Okay, whenever this happens, you need to remind yourself of what? No. Yes?
We remind we should use, it's like going together, we need to use the chain.
The chain rule, yes. Whenever you see, this is not the sine of x. This is sine, but of another function, not just x. Yes? I don't know what has happened to your brain, but hopefully
Is it like,
you don't have any concussions, yes?
is it?
So what is, if I want to calculate the derivative? So I didn't talk about this because I really intentionally want to see how much you know. Do you remember? This is the only formula you get in the table, but it doesn't mean this is the only function we can differentiate. If I give you sine u, where u is a function of x, sine u is not in your table. It is in your table only if u is exactly x. But if u is not exactly x, this function is comparable to what? Is comparable to sine x, which is in my table, and I know how to differentiate it. The differentiate becomes cosine x. So this means that I know how to differentiate this. I follow the same rule, pretending u is x, so it becomes cosine u, but it is not finished here. You have to multiply by u prime. So this process is always the same. So whenever you learn a formula, this doesn't mean that you just know how to do this one. If you can use chain rule to make more complicated functions, of course you can use it. This process is always the same. I am repeating it itself over and over, okay? Repeating it over and over. So you see, I know that I want to know the derivative of sine u. U is a function of x. I compare it with what I have. I can compare it only with this. I know the answer to this. Then I would say the answer to this is as before, pretending u is x, but I have to multiply by u prime. And this is always the case. You don't need to remember anything. You just multiply by u prime. Okay? So now if I go back and I want to calculate sine x, sine of pi over 2 minus x derivative, I don't see it in my table, but if I am wise enough to consider this u in my head, then this turns out to be sine u. Sine u is comparable to sine x. Sine x, I have it in my table. So this means that this also follows the same rule, but an extra u prime. Yes? Okay, so let us just do that. So what can I write? U is this, I use this one. So it becomes cosine of pi over 2 minus x. But it is not finished. Yes? I have to multiply by u prime. Yes? Okay, now tell me, can I write this expression simpler? That is sine of x, because pi over 2 minus x is complement to x, so cosine of one of them is equal to sine of the other one. But what is the derivative here? It's minus 1. And you multiply minus 1 here, so it becomes minus sine x. So this derivative is minus 1. And the answer is minus sine x. So if I want to fill it up, it becomes minus sine x. Yes? Okay, so we learned simple formulas. Derivative of sine is cosine. Derivative of cosine is minus sine. Okay. Okay, before continuing, let us solve some problems. Okay, so I start with a very simple example. Differentiate. Okay, so let me write very simple one first. F of x is equal to 7 sine 4x. So I want to differentiate this function. So what should I do? I take the derivative. I know this rule, I already know about it. It's a multiplicative constant, so I don't do anything with the multiplicative constant. I concentrate on taking the derivative of 4x prime. By the way, you don't have to put pair of brackets. Let me tell you, if you write sine x plus 4, or if you write sine 4x, here people understand 4x should be in pair of brackets. But if you write this, people will not read it as this. People read it as sine x plus 4. Okay, so be careful about that. And I think in your book and even in the national exam, they don't put the pair of brackets if you have a multiplication. But of course, let us just make it more clear. Okay, so that is what I'm supposed to do. But the problem is that this formula is not directly in my table. Yes? But I need to think about the chain rule and that rule. So what do I take for u? What do I take for u? Yes, I take 4x to be u. Is it a good choice? Yes, because if I take this to be u, you see I'm repeating this over and over again, hopefully you'll learn. This is comparable to sine x. The rule for sine x is cosine x. So the rule for sine u becomes cosine u times u prime. Okay, so what I do, I will write it as 7. And then this becomes cosine u. Yeah, by the way, I don't need to put this bracket. So it becomes cosine u, but multiplied by u prime. But what is the answer to u prime? 4, and it is better to multiply it here. So it becomes 28 cosine 4x. So that is the answer to the derivative of that function. Yes? Is that clear? Okay, let me give you another example. So number 2. So what do you think about this? G of x is equal to, let me write it as 5 sine 3x. Yeah, it's good. And then minus, let me write 4 cosine x over 2. And you don't need to write the pair of brackets for this either, so you can just simply write x over 2. Okay, so we want to differentiate this function. So if you don't mind, let me wait for you 2 minutes so you can do it yourself, and then I will correct you if you have done something wrong. Okay, so how should I do that? Let us do it. I write all the details, but very quickly. So if I want to take the derivative, I know what to do. This is the difference between two functions, so I differentiate this one minus this one. But these are multiplicative constants, so I don't do anything with them. I only concentrate to take the derivative of this minus 4, the derivative of that. Yes? And then what I'm supposed to do, again, the same story. This is not exactly in my table, so I have to take this one u in my head. So the answer becomes 5. The derivative of sine of u is cosine of u, but it is not finished. I have to multiply by the derivative of that. And minus 4, the same story here. The derivative of cosine in my table, I take this one u here. So the derivative of cosine u is comparable to the derivative of cosine x. The answer to this is minus sine x. So the answer to this becomes minus sine u, but u prime. So this becomes minus sine u, but multiplied by u prime. And then I have to do simplifications. The derivative of this is 3. I multiply it here. It becomes 15 cosine 3x. Minus times minus is plus. What is the derivative of x over 2? 1 over 2. I multiply it here, it becomes 2, and then I have sine x over 2. That is your answer. Okay, so if you got it right, it means that you know it. But usually, based on my experience of teaching, usually this is the problem students make mistake. I don't know why. So if you don't mind, let me put a star here so that if you want to review, you can see this. I will wait for you, of course, to see how do you do that. So let me write h of x this time. I would write it as, let me make it simple, sine, I put a 5 on top, mean the power, and then I write 3x here. Sine 3x to power 5. So then I want you to differentiate this. I will wait for you. Okay. So usually the mistake that some students make is this. They take this one to be u. But this is not working. Let us see why. If I take this to be u, then I face sine to power 5u. This is comparable to what? Sine to the power of 5x. But this is not in my table, so that's not a good choice. Okay? If that is not a good choice, so that is not a good choice, because taking this to be u gives me a function which is comparable to this one, but this one is not in my table. I don't have that power of 5 there. So what is the other choice then? To take whole thing to be u. Is it a good choice now? So that was not a good choice. Is it a good choice? Yes, because if I take this u, then it becomes u5. u5 is comparable to what? x5. Do I know the derivative of x5? Yes. It becomes 5x to the 4. So the derivative of this one follows the same rule, but the difference is that it has an extra u prime. Okay, so very simple. So if I want to do that, h prime of x becomes what? What happens? 5u to the power of 4. So 5u to the power of 4, but multiplied by u prime. Yes? The problem is not finished because there is a prime left, so I have some copy paste to do. But now, for this one, I'm in trouble because this is not exactly in my table. Okay? What is, I have to take this one to be u. Is it a good choice? It was not a good choice in the beginning, but it is a good choice and the only choice here. Why is it good? Because if I replace this with u, I will have sine u. It is comparable to sine x. Sine x is cosine x. This one becomes cosine u times u prime. So that's good. So if I want to take this one, the derivative of sine u becomes cosine u, which is cosine 3x, but it is not finished. I have to multiply by the derivative of 3x. And then finally, the derivative of 3x is just 3 multiplied here, it becomes 15 sine to the power of 4 3x times cosine 3x, and that is your answer. I don't know, for some reason, students usually write 15 cosine 3x to power 4. Yeah, that's the reason. I don't know why, but this is statistics, so be careful about it. Okay, any questions so far? Okay, so let us, if you don't mind, let us go to the third question mark. I want to ask you again, okay? Okay, so if you don't mind, let me review very briefly about what ln is. So do you know we have a logarithm? What is a logarithm? A logarithm, you have a number in front of the log, and then you have a number here, which is called the base. The properties of these numbers, a should be positive, b should not only be positive, but it is not allowed to be 1. So under these conditions, this symbol is defined. And when we say this is x, what do we mean by that? It means b to the x is a. Yes? That's the meaning. So in other words, when I say logarithm of a to the base b, it is asking me what that number is, x, so that b raised to that power becomes a. So for example, if I ask what is logarithm of 16 to the base 2, it is asking me which is the number so that 2 to that number becomes 16. In this case, extremely simple, is what? 4. Why? Because 2 to the power of 4 is 16. Of course, if you ask me what is logarithm of 15 to the base 2, it will ask the same question, but I cannot read it from on top of my head, yes? Because I don't know what is that number so that 2 to that number is 15. But if I want to know that, I have to use my calculator. But I don't want to go to the details of logarithm today. If you have forgotten, you can see one of my videos or some of my videos that I was talking about this and I've recorded, okay? In Math 3C especially. Okay, but do you remember, if this base is 10, we don't write it. So for example, if you see logarithm of 1000, because every logarithm has two numbers involved in it. One, the number in front, one, the number serving as the base. But if you see you have only one number in front, automatically, by convention, it means that the base is 10. So if I want to answer this question, I have to ask this question. What is that number so that 10 to that number becomes 1000? So simply the answer is 3. Okay? There are some properties of logarithms. I don't want to go through them. But one thing that I want to say is that what is ln, which is called the natural logarithm? So whenever you see ln and then you see a in front, this means, semicolon means it is equal by definition. This is the same as a log of the same number, but the base is e. Instead of writing logarithm, if the base is 10, we just don't write it. If the base is e, instead of writing log to the base e, we simply write ln. So in other words, you can imagine that ln means log to the base e. But what e is, do you remember? E is the Euler number. We discussed about this extensively in Math 3C. If you have forgotten, you can just watch the video. So the Euler number, and it is an irrational number, approximately 2,72. It's irrational, so it means that these decimals will continue forever. This number, together with pi and I and 1, are fundamental constants in mathematics, yes? E is the Euler number, pi is this 3.14 something. I is the imaginary unit. We will study that in the last chapter, and 1 is of course 1. So these are fundamental constants of mathematics. It is one of them. Okay? So when I say logarithm, when I say ln of a is equal to x, what is the meaning? When I say ln of a is equal to x, this means e to the power of x is a. Yes? So that is the meaning. Okay, but now this was just a very, very brief review of the natural logarithm. But my question is not this, of course. This we have already studied extensively. But the question is that if I have this function, by the way, can x be negative? You see, for every logarithm, the number sitting in front should be positive. So this is not defined if x is negative. So it means that whenever you see this function, implicitly it means that x is positive. Otherwise, so in other words, the domain of this function is this. Okay, so the question is now, what is f prime of x? Okay, now I want to hear from you what we are supposed to do. I want to find the derivative of this logarithmic function. Use the definition, but that would be an obstacle in front of us. So if I want to write the definition, this becomes the limit of f of x plus h minus f of x over h when h goes to 0. Okay, so what happens? This becomes the limit. F of x is ln of x. And then I have ln. I replace every x with x plus h. Okay, but this is something, in principle, we can find a way to solve this limit. I think we can solve it rigorously if you remember a lot of things about the E number and how E is defined in the first place. So you can solve it, okay? But I don't want to go through it because there is a better way, much faster way of calculating the derivative, okay? Okay, so even though in principle this method works, but it is not as good as what I want to present now. Okay? Okay, let us see how can I do that. So I want to answer what is y. So I will introduce that y is ln of x. I want to calculate y prime. Okay, can you tell me what do you think I will do if I don't want to use the limit? For example, for the case of sine, I use the limit. But for the cosine, I reduce it to a sine and use the chain rule. But what do you think would be an alternative here? Of course, one way is to calculate this limit. Yes?
E to the power cosine.
E to power?
E to power y and e to power ln of x.
No, e to power ln of x gives me x. But then what? But that's not a bad start. But then you don't know why. So you just say something without knowing why. Okay, so what we do is this. So what he said is correct. So if I ask you e to power ln of x, what is the answer? Do you remember? This is x. We had this before. And by the way, it is very clear here. Why? Because you say ln of a is x, it means e to power x is a. Okay, and if I ask you what x is, you tell me x is ln of a. So this means e to power ln of a is a. It's just the definition of the ln. Okay, but instead of a, I just write x. So that is correct. If this is equal to this, then it means that the derivative of the left-hand side is also equal to the derivative of the right-hand side. Okay? The derivative of the right-hand side is extremely simple. Is 1. But if I want to take the derivative of this, what should I do? This is not in my table. The closest formula that I have in my table is e to power x. Okay? So I have to take something to be u. What should I take to be u? Yes? ln of x. So I will take this one to be u. Is it a good choice? Yes. Why? Because if I take that one to be u, then I will have e to power u. This is comparable to e to power x. Do I know the answer to power x? Yes, it is the function itself. So then what happens for e to power u? It becomes the same rule, but I have to multiply by u prime. Okay? So let us just do that. E to the power of u prime becomes e to the power of ln of x. It is not finished, multiplied by u prime. Yes? But this is exactly my question mark. I want to answer that. But you know something, if I ask you write this simpler, what do you say? It is still on the board. X, e to power ln of x is x. So what I see x multiplied by my question mark, ln of x prime, is 1. I am looking for the question mark. So the question mark is 1 over x. So this means that ln of x prime is 1 over x. And might be you don't even expect this, because the derivative of every function so far is of the same type. What do I mean by that? For example, here I have a constant function, its derivative is 0. 0 is still a constant. Here I have a power function, the derivative is a multiple of another power function anyway, it's a power function. Here I have exponential, the derivative is exponential, 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 trigonometric, 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 trigonometric. But here, this is the first time that I have a logarithmic function, its derivative is totally different, is 1 over x. So this is my last question mark that I'm supposed to answer today. Yes? So this is 1 over x. Okay? But again, as I told you before, extremely important. You will only get this formula in the formula sheet, but you need to understand the chain rule version of that yourself. What is the chain rule version of that? Let me write it here for you. What happens if I don't have x, if I have u? What is the answer? It follows the same rule as if u is x, so it becomes 1 over u. But it is not finished. I have to multiply it by u prime. And this is common. People, instead of writing it like this, they write it as u prime over. So if you want to take the derivative of ln of another function, not just only x, you take the derivative of this, put it in the numerator, and then divide it by u itself. So it is no longer a logarithmic function at all. Okay, so let me solve some examples here. I will give you two examples. One I will solve, one I will wait for you, because that is not hard. Then I will solve the more interesting problems, of course. So example, differentiate. So let me give two examples. One, f of x is equal to ln of x squared plus 1. The second one, I'll wait for you, okay? G of x is ln of x squared plus 5x plus 10 to the power of 3. ln is also like sine and cosine. You put the power in the middle between the symbol and the argument. Okay, so let us just do this. For this one, I hope that it's very clear what to do, yes? This is ln. The closest formula to my purpose is the last row, but unfortunately that is only ln of x. This is not ln of x. So this means that I have to apply the chain rule. So what should I take as u? I will take this one as u. Okay, when I take this one as u, I have ln of u. ln of u is comparable to ln of x. ln of x is 1 over x. So ln of u is 1 over u, but multiplied by u prime. The reason that I write this, because you have only access to this one. I want to make sure that you understand. Okay, so what I do, I take the derivative. ln of u is 1 over u, which is this one, but it is not finished. I have to multiply by u. And of course, this is extremely simple. It becomes 1 over x squared plus 1. The derivative of that is 2x. You can stop here, but I prefer to simplify it. I mean, write it more compactly. This is the answer. Okay? Now I wait for you to do that one for me. Okay, I hope that you could solve that one, yes? So what we should do here, so what we are supposed to do. Here, of course, you see the function is not directly in your table. So here you might think that I take this one to be u, but this is not a good idea, because if I take that one u, it will read ln to the power of 3u, which is comparable to ln of x to power 3, but this is not in your table. So that is not a good option. So the only thing that is left for you is to take the whole expression to be u. Is it a good idea? Yes, because then you will have u3. u3 is comparable to x3. x3 is 3x squared, so u3 becomes 3u squared u prime. So then g prime of x becomes equal to 3 u squared means ln of the same thing, but instead of power 3, power 2. But the problem, you have to multiply by the ln of, you have to multiply by u prime. Okay? But now, copy and paste this part. Then what should I do? This one I need, it is not in my table, so I have to do the same trick. I have to choose something to be u, and I hope that you agree with me. This one, this is good. Why? Because then you will have ln of u, which is comparable to ln of x. ln of x is 1 over x, ln of u is 1 over u, but multiplied by u prime. So this becomes 1 over u, but it is not finished. You have to multiply by this. And then, of course, this is extremely simple to do. But if you don't mind, let me write this more compactly. So I put this in the numerator. And then this in the denominator. But the derivative of this is extremely simple. It's just 2x plus 5. And that is the final answer that you are supposed to provide. What?
Is there any way to make this look nicer?
No, I don't see any way. Okay, any questions? Okay, so let us do one example, level 3 problem here. So if I go here to the book, let us do, this is the only level 3 problem that you have here. Of course, I want to wait a little bit for you. You are supposed to determine the value of the constant k so that this line becomes tangent to the curve of y equals to ln of x. You couldn't solve this problem before because it needs the derivative of ln, which we just learned. I think it's a very good question, even though it is stated very simply, but let me give you time to see how you think about the problem. Fine-tune k so that this becomes tangent to this curve. Okay? Yeah. This problem needs a good understanding. So this really, I think, is a good problem to call level 3, not because the algebra is involved, but because you have to have a good understanding conceptually. Okay, so let us try to understand the problem from actually using GeoGebra a little bit, and then. Okay, so what is the problem? The problem, let me draw the graph of ln of x for you. So using GeoGebra, y is ln of x. Yes, that is the graph of ln of x. Okay. And then, of course, this line that you see here is not a fixed line. Its y-intercept is 2, but k changes. When k changes, it means that the line starts rotating, yes? Because the slope changes. We can do this using GeoGebra like this. So we go and type y equals to k. Let me use multiplication here, x, and then plus 2. As soon as I press enter, GeoGebra provides for me a slider. Okay, so automatically by default it goes from -5 to 5, but we don't need negative values here because I don't think negative values will work here. So, but let us see. I just take this slider and slightly moving it around. So you see that this is actually going in that direction. So I don't know, it is not tangent now. So let us go to the opposite direction. You see, it rotates and rotates. At some point, it becomes tangent to this green, but I cannot fix it with my hand. It goes faster than I expected. Okay, so let me use this. Something like that. If I don't know if I can show it to you, but if I increase this, no, increase does not work. It goes very fast. I mean, let us play it around. So you see, at some point, by changing the k value, this line changes its slope. It becomes, of course, faster and faster. Oops, I cannot keep it. But I hope that you agree with me. At some point, it will touch this graph. Okay? That is exactly the value we are supposed to find. I don't know why this is not working. So I can change the increments, but I don't want to waste time because we don't have that much time. But I hope that you agree with me. If I start changing the value of k, for exactly one value for k, the black line becomes tangent to the green curve. That value of k we want to find in this problem. Yes, is that clear? Okay. So let us try to imagine. How do you think about the problem? These problems are conceptual. So you have to, I don't want to be precise, but this is more or less the graph of ln of x using GeoGebra. And then this point is 1, 2. Okay, and this is my line. Okay, one of these lines is supposed to be tangent to this graph. One of these lines. This point is of course 2 because the y-intercept is 2, but the k value changes at some fixed value of k, I will get my tangent point. And I want to find that k. So what is your idea? How should I find that? Yes?
We can say that in this case it's kind of strange, but if we imagine these as two functions,
Yes?
l of x and kx plus 2, let's call them f of x and t of x. We know that their value, we know that there exists some a, or will exist some a, such that the values of these functions are equal and their derivatives are equal.
Yeah, exactly.
Then we have two
So
equations.
we can make it simpler because if I ask you to find the k value of the tangent line, what do you need? You need to know the derivative, which we know today. We also need to know the x coordinate of the point of tangency, which we don't know, because we don't know where it will touch. Okay? So I can pretend I know, let me call it A, and then what will be the coordinates of this point? Let us consider it on the curve. Of course, as Rasmus said, it is also on the line. We will use it at some point. Okay? So I would pretend that I know this. So A and the y value is ln of A because it lies on the curve. And of course, as you said, that's also correct. It lies on the line as well. But I don't like the line because the line is missing. It has a missing part. This doesn't have any missing part yet. So I have only one unknown. If I put it there, A is not known, K is not known. Of course, I have to deal with it at some point. But let us start with this. Okay. I pretend that A is given to me, and I find the K values. How do you do that? You take the derivative of your function. Today we learned that. It's extremely simple. And if I ask you what is the k value should be what? Replace x with the x coordinate, which is 1 over a. This is the k value according to my calculation, but that is k value according to what is given to me, because this line is supposed to be the tangent line, so its k value should be the k value I calculate from here. Yes? Okay, but I cannot say I found k. Yes, because k is related to a, but a is still missing. So what can I do now? As Rasmus said, this point is not only on the curve, but also on the line. So it means that the coordinates of this point should also satisfy the equation of the line. It means that if instead of y, I put the y coordinate, and instead of x, I put the a coordinate, this should work. Yes? Yes? But I found the relation between k and a. What is this relation? K times a is what? 1. So it was very simple. So this I put 1, ln of a becomes 3. And I am looking for a momentarily, it becomes e to power 3. So a is e to power 3, but the problem wants k. Okay, k is 1 over a, so this means that k is 1 over e to the power of 3, which is e to the power of negative 3. And this is why we actually couldn't guess. Okay, but if you want, I can come back here to the GeoGebra, and now we know that the k value is what? E to the power of minus 3. So if you don't mind, let me type it here. Y is equal to e to the power of minus 3. So let me use this virtual keyboard. Oh, sorry. E to the power of minus 3. Yes, I don't need the brackets here. And then go down and put x and then plus 2. Okay, so that is why we couldn't find it, but now by calculation, we really found that. You see, I couldn't fine-tune it with my hand, but now when we did the calculation and put that number here, this new line, if you want, I can change the color so that you see this is this line. Yes. So this red line is this one, and it is really tangent to that curve, which I couldn't fine-tune because it was so fast for me to catch it. So you see, these problems, I really like them because the algebra is very minimal, okay? But this is conceptual. So the people who can solve these problems, they have a better understanding. So if you couldn't, try to see why you couldn't and take lessons from it. Okay, any questions? Yes?
Since E is rational,
Mhm.
I mean, graphically, when you express it, like, this graph can't actually express something that tilts within a rational number, right?
No, what they do in the software, I don't know. But of course, they can make it. So this is probably not the real tangent, but we cannot deviate it from the exact tangent.
Yeah, so,
But it doesn't matter.
now I get it, but I mean, so, well, I guess a line with a slope of E is just a theoretical thing that you can actually physically express it.
Yeah, of course. It's like the square root of 2. So what is the square root of 2? Is that number whose square is 2. But how should we know that number exists? We have some axioms for real numbers. If we accept those axioms, then this will be a theorem that there is one unique number whose second power is 2. There is a unique positive number. But that is it. Yes? Okay. So I think it's a good point to stop here if you don't have any questions. Thank you.